Recently, Andrej Karpathy sat down with the No Priors podcast and talked about a huge number of things, including Waymo versus Tesla, the advantages of humanoid form factors, and the magic of the transformer architecture. Let's take a look. Hey y'all, it's Dr. Know-It-All coming to you back from Athens, Georgia again. I was just at the Everything Electric Vancouver event. I have to say that Robert Llewellyn and crew put on a great show. It was fantastic seeing a bunch of you there. And of course, if you missed me there this year, be sure to check me out next year. I love Vancouver, I love the event, so odds are I will be back. Anyway, just before I left for that trip, Andrej Karpathy sat down with the No Priors podcast and did a video. I haven't had a chance to react to it yet. I have to say that this video is chock full of information. Of course, I'll leave a link to it in the description so you can watch the whole thing. What I've decided to do is break this into two parts. Today's video encompasses the first 20 minutes or so, or about the first half of the video, and focuses a lot on Tesla and a lot on Optimus and full self-driving and everything. The second half focuses more on a little bit more general topics and also AI and education. Andrej Karpathy has started a company on that if you don't know. And of course, in regards to all of this, including the education part in particular, Andrej, if you're ever interested in coming on my YouTube channel, I would love to have a sit down chat with you. Let's make it happen. All right, so first let's start with a story from Andrej about taking a ride in a Waymo a full decade ago, and how amazing that ride was in 2014, and how it's taken a full decade for Waymo to get from a demonstration drive to the ability to actually sell rides in the San Francisco area.
Can take around here. So Waymo in San Francisco here is of course very common. Probably you've taken Waymo. I've taken it a bunch and it's amazing and it can drive you all over the place and you're paying for it as a product. What's interesting with Waymo is the first time I took Waymo was actually a decade ago, almost exactly, 2014 or so. And it was a friend of mine who worked there and he gave me a demo. And it drove me around the block 10 years ago. And it was basically a perfect drive 10 years ago. And it took 10 years to go from like a demo that I had to a product I can pay for that's in a city scale and is expanding, etc.
How much of that do you think was regulatory versus technology? Like, when do you think the technology was ready? Is it recent?
I think it's technology. You're just not seeing it in a single demo drive of 30 minutes. You're not running into all the stuff that they had to deal with for a decade. And so demo and product, there's a massive gap there.
So as Waymo and Google, of course, that bought Waymo found out, it's one thing to get to that 80 or 90% correct, and quite another thing to get to the 100% or 99.99 something percent correct that will allow you to go from a demo drive to really releasing a product. Of course, we've seen Tesla over approximately the same amount of time. They started a little bit later in around 2015 or so, and Andrej, of course, was instrumental in this. He and a recruiter at Tesla were basically the people that put together Tesla's FSD AI team. So, you know, that's how instrumental he was in this. So he really knows what he's talking about here. But he talks about how going from getting it, you know, pretty well right to do a demo drive to being able to do something that you can actually trust, where humans can take their hands off of a 3,000 plus pound death machine on wheels, you know, to be able to go from the point of doing a demo drive to the point of being able to do this as a full release and to charge commercial customers for it is a very, very long road. It all comes down to edge cases, corner cases, whatever you want to call it, but all of the little stuff. So in other words, 90% of what you encounter, or 95% or 99%, all of that stuff a car can handle, and we see Teslas do it all the time. I mean, I drive around in one. Andrej talks about driving around in FSD 12.5. whatever, and how amazing it is. But even when you get to the 99.99 something percent of the time it can handle it, what happens with that 0.001% of the time when it can't? Those are the issues that keep the Waymo engineers and the Tesla full self-driving engineers up at night, because it's the kind of stuff you have to solve before you can commercially release this, or alternatively, you have to have some sort of graceful failure system where things can back out and you can allow a human to take over, or the car can pull over safely at the side of the road, or something like that. So if you think it's easy to go from a demo to a true commercial product, you are definitely wrong, and you haven't really developed anything for commercialization. It is very, very difficult. More on that in a minute, but first, with AI potentially lengthening our lifespans by decades, it's even more important than ever for us all to take care of our skin to keep it looking and feeling healthy no matter our age. The trouble is, I'm no skincare expert. That's why today's sponsor, Geology, is a great skincare partner. They have scientifically created a number of skincare solutions based on your own unique age, skin type, and other factors. You take a simple quiz, and Geology's smart algorithms determine what you need for optimal skincare. I'm care routine number 30, and it's great for my skin. And it's great that the daytime cream has built-in SPF 15 sun protection, so when I'm out and about in the lovely early fall weather, my face is protected from the Georgia sun. Geology is scientifically based, built around proven ingredients, trusted by dermatologists, and people love Geology. It's gotten over 10,000 5-star reviews and turned many a skeptic into a believer. And best yet, Geology is simple, efficient, and very effective. You take their quiz, you get their personalized skincare routine mailed directly to you, you follow their super simple instructions in the morning and at night, and you get better, younger-looking skin in no time. And just for you, my viewers, Geology is offering an amazing 70% off their skincare trial set. Be sure to click my link below to get this amazing deal, or feel free to check them out at Target or on Amazon. I love Geology because it's powered by facts, not fads. It's a simple-to-use routine designed just for you and built around a handful of powerful, proven ingredients that have been trusted by dermatologists for decades. So what are you waiting for? Be sure to take the Geology quiz and save 70% off your skincare trial set. And now let's get back to it. Next up, Andrej talks about Waymo versus Tesla and who is actually ahead.
It will look in a similar way for AGI when we sort of get it. And then staying for a minute in the self-driving space, I think people think that Waymo is ahead of Tesla. I think personally Tesla is ahead of Waymo, and I know it doesn't look like that, but I'm still very bullish on Tesla and its self-driving program. I think that Tesla has a software problem, and I think Waymo has a hardware problem, is the way I put it. And I think software problems are much easier. Tesla has the deployment of all these cars on Earth, like at scale. And I think Waymo needs to get there. And so the moment Tesla sort of like gets to the point where they can actually deploy this and it actually works, I think it's going to be, really incredible. The latest builds I just drove yesterday, I mean, it's just driving me all over the place now. They've made like really good improvements, I would say very recently.
Yeah, I've been using it a lot recently and it actually works quite well. So.
It did some miraculous driving for me yesterday, so I'm very impressed with what the team is doing. And so I still think that Tesla mostly has a software problem, Waymo mostly hardware problem. And so I think Tesla, Waymo looks like it's winning kind of right now, but I think when we look in 10 years and who's actually at scale and where most of the revenue is coming from, I still think they're ahead in that sense.
So of course, Andrej worked for Tesla for a period of time, but of course he also worked for OpenAI and other companies and hasn't been at Tesla for quite a while. So he is speaking as an outsider here, but what he's saying here is a really good counterpoint to those who argue that Waymo is clearly ahead because they're charging for full self-driving in very, very geofenced, very limited areas. Tesla's is a wide-scale solution, and nobody else has the scale, the number of vehicles that Tesla has on the road. And if they're able to overcome the software problem, as Andrej says, I really like that. Waymo has a hardware problem. They have a very expensive car. They have a lot of pre-mapping they have to do. There's a lot of stuff that has to happen. And then the software is relatively easy. And he'll talk more about that later in this video, but we'll get back to that. But Tesla has more of a software problem. They've decided on a specific set of hardware, and in the vehicles itself, it's not that expensive. So it's actually relatively easy to put those out at scale. And there are millions of them on the road around the world right now. So if Tesla can overcome the software problem, they already have the hardware at scale. It's much, much easier to ramp up software than it is hardware. Tesla has the advantage. That's what Andrej's saying here. And speaking of sensors, Andrej actually talks about the sensors and how Tesla does use expensive sensors, but as he said, they arbitrage their sensors.
Actually, what's really interesting about that is I'm not sure that people are appreciating that Tesla actually does use a lot of expensive sensors. They just do it at training time. So there are a bunch of cars that drive around with LiDARs. They do a bunch of stuff that like doesn't scale, and they have extra sensors, etc. And they do mapping and all this stuff. You're doing it at training time, and then you're distilling that into a test time package that gets deployed to the cars and is vision only. And it's like an arbitrage on like sensors and like expense.
Yeah.
And so I think it's actually kind of a brilliant strategy that I don't think is fully appreciated. And I think it's going to work out well because the pixels have the information. And I think the network will be capable of doing that. And yes, at training time, I think these sensors are really useful, but I don't think they're as useful at test time. And I think you don't.
So let's think about that for just a second. Tesla uses expensive sensors. They also have incredible training compute as well, on the order of billions of dollars worth of training compute that's in these giant data centers. They arbitrage all that very expensive hardware in order to, as Andrej says, distill down the essence of what needs to happen into a relatively small package that can run on a mobile computer and can run with only 8 cameras as input on a vehicle and do it in real time. So they're arbitraging the very, very expensive training, the very expensive hardware that they put on vehicles in order to do the training, in order to make the inference work in real time on low-cost hardware. That is pretty genius. Next up, Andrej talks about one of his favorite topics, which is software 2.0 eating software 1.0. Software 1.0 being the older heuristic-based code, software 2.0 being more end-to-end neural networks. If you haven't caught any of my videos on software 2.0, check them out up here.
Yeah, I think that was always like the plan from the start, I would say, at Tesla, as I was talking about how the neural net can like eat through the stack. Because when I joined, there was a ton of C++ code, and now there's much, much less C++ code in the test time package that runs in the car. Because there's still a ton of stuff in the backend that we're not talking about.
By the way, that would be arbitrage right there.
The neural net kind of like takes through the system. So first it just does like a detection on the image level. Then it does multiple images, gives you prediction. Then multiple images over time give you a prediction. And you're discarding C++ code. And eventually you're just giving steering commands. And so I think Tesla is kind of eating through the stack. My understanding is that current Waymos are actually like not that, but that they've tried, but they ended up like not doing that is my current understanding, but I'm not sure because they don't talk about it.
So note that he's saying that Waymo, as far as he understands, uses much more heuristic code. In other words, if then, that kind of code. And I'm quite certain, even though Andrej didn't say it, that he agrees with me that that is not the way to solve full self-driving in a general case. It needs to be neural networks end to end or neural networks all the way down. So, you know, he's too nice to say that, but I'm not. I don't think Waymo has a path to scaling based on what they're doing right now.
I do fundamentally believe in this approach. And I think that's the last piece to fall, if you want to think about it that way. And I do suspect that the end-to-end systems for Tesla in, like, say, 10 years, it is just a neural net. I mean, the videos stream into a neural net and commands come out. You have to sort of build up to it incrementally and do it piece by piece. And even all the intermediate predictions and all these things that we've done, I don't think they've actually like misled the development. I think they're part of it because there's a lot of solid reasons for this. So actually, like end-to-end driving, when you're just imitating humans and so on, you have very few bits of supervision to train a massive neural net. And it's too few bits of signal to train so many billions of parameters. And so these intermediate representations and so on help you develop the features and the detectors for everything. And then it makes it a much easier problem for the end-to-end part of it. And so I suspect, although I don't know because I'm not part of the team, but there's a ton of pre-training happening so that you can do the fine-tuning for end-to-end. And so basically, I feel like it was necessary to eat through it incrementally, and that's what Tesla has done. I think it's the right approach, and it looks like it's working. So I'm really looking forward to it.
If you had started end-to-end, you wouldn't have had the data anyway. That makes sense, yeah.
So this is a really important point. What Andrej is talking about here is a sparse reward system. You can imagine, like, take a game where you only know if you have done a good job in the game at the end of the game. You could even say chess is something like that. Relatively sparse reward system, although they've come up with a point system and everything. But you can just say, like, you have to play the entire game of chess to find out if you won or lost or drew in the game. And that's relatively sparse if you don't have any intermediate steps. And that's kind of what you're getting with full self-driving, except on steroids because it's real life. So it's very, very sparse to know whether you did a good job or not. And what Andrej's saying here is that rather than wasting time, you know, as Tesla was working with all this heuristic code, working on figuring out a data pipeline, working on all of these other steps, what he's saying was those were necessary steps to allow software 2.0 or the end-to-end neural network to eat through software 1.0. So he's predicting it's going to take 10 years. That's really interesting. I would imagine that we're probably looking at more like 4 or 5 years. So he's less optimistic than I am. But of course, he has much better credentials. So I guess maybe we can go with him. But certainly we're looking by 2030 to 2035. We should be looking at most vehicles that are using this sort of system be able to drive themselves. And of course, Tesla will be very much in the lead on that. Next up, they turn to humanoid robots and specifically Optimus. And Andrej has asked what transfers from full self-driving to Optimus. His answer probably won't surprise you.
Starting here, what transfers?
Basically, everything transfers, and I don't think people appreciate it.
Okay, that's a big claim. It seems like a very different problem.
Cars are basically robots when you actually look at it.
Okay.
Cars are robots, and Tesla, I don't think is a car company. I think this is misleading. This is a robotics company, robotics at scale company, because I would say at scale is also like a whole separate variable. They're not building a single thing. They're building the machine that builds the thing, which is a whole separate thing. And so I think robotics at scale company is what Tesla is. And I think in terms of the transfer from cars to humanoids, it was not that much work at all. And in fact, like the early versions of Optimus, the robot, it thought it was a car, like because it had the exact same computer, it had the exact same cameras. It was really funny because we were running the car networks on the robot, but it's walking around the office and so on.
Oh, amazing.
And like it's trying to like recognize drivable space, but it's all just walking space now, I suppose. But it actually kind of like generalized a little bit, and there's some fine tuning necessary and so on. But it thought it was driving, but it's actually like moving through an environment.
So that's a really amusing story, but also incredibly insightful. Basically, they were able to literally transplant the brain out of a car into an early Optimus prototype, and it worked. And that is remarkable. In other words, it didn't work perfectly because it was looking for roads, it was looking for, cyclists and things like that, and traffic lights probably. So it thought it was a car, and that actually sounds like the name of a short story or something, the robot that thought it was a car. That'd be a really fun short story. Maybe me and ChatGPT should write that sometime. But anyway, the point is that full self-driving was able to literally transfer directly into Optimus, and it worked at a basic level. Obviously, you need to fork it off so Optimus can get its own version of the software eventually, but it's really cool that that works. And then, of course, Andrej talks about scaling. Who else is going to be able to build these things, not just the brains, but also the hardware at scale? And Andrej is very, very adamant about the fact that Tesla has a huge advantage at that. And speaking of scale, Andrej talks about how rapidly Tesla was able to scale because of the engineers and their experience in building things already, and of course their flexibility and enthusiasm.
All the stuff just showed up so quickly, and all these CAD models and all the supply chain stuff, and I just felt like, wow, there's so much in-house expertise for building robotics at Tesla. And like, it's all the same tools, and they're just like, okay, they're being reconfigured from a car, like a Transformer, the movie. They're just being reconfigured and reshuffled, but it's like the same thing. And you need all the same components. You need to think about all the same kinds of stuff, both on the hardware side, on the scale stuff, and also on the brains. And so for the brains, there was also a ton of transfer, not just of the specific networks, but also all of the approach and the labeling team and how it all coordinates and the approaches people are taking. I just think there's a ton of transfer.
Next, Andrej gets into the big ticket question of the day about embodied AI, and that is, should these robots be released to customers first or to factories first? And Andrej thinks it should actually be you if possible. In other words, Tesla's best first customer is actually themselves.
So I think the best customer is yourself first. And I think probably Tesla's going to do this. I'm very bullish on Tesla, if people can tell. The first customer is yourself, and you incubate it in the factory and so on, doing maybe a lot of material handling, etc. This way, you don't have to create contracts working with third parties. It's all really heavy. There's lawyers involved, etc. You incubate it, then you go, I think, B2B second. And you go to other companies that have massive warehouses. We can do material handling. We're going to do all this stuff. Contracts get drafted up. Fences get put around, all this kind of stuff. And then once you incubate in multiple companies, I think that's when you start to go into the B2C applications.
So of course, Bernd Bornisch disagrees about this because he thinks going into the consumer space is the best first application. But Andrej Karpathy agrees with most people that the best first customer is yourself, because you don't have to do a lot of legal wrangling about how it's going to be implemented. The second best customer is, sort of factory, logistics, warehouses, things like that, where you can sort of fence off the robots and there's a safety factor and they can do their thing and learn. And then it's only after that you actually introduce it into the home, into consumer markets, which are much less constrained, and you can't really control how the robots are going to be interacted with. So I tend to agree with Andrej that I think that that's the best path forward, unless you have a robot that's so safe that it basically can't hurt anybody, which is what EVANNEX is going for. So it's very cool to see that there are a range of different strategies coming out, because that means that we have more chances to see robots in the home and in the factory at the same time from different companies potentially. Next, they ask Andrej about why the humanoid form factor. In other words, why not make specialized robots for each individual type of task instead of just making a generalized robot?
I think people are maybe underappreciating the complexity of any fixed cost that goes into any single platform. I think there's a large fixed cost you're paying for any single platform. And so I think it makes a lot of sense to centralize that and have a single platform that can do all the things.
So just real quick, an analogy would be like automobiles. Like, instead of making 100 different automobile models, just make 1 or 2 for, each category that these automobiles are in, which is Tesla's general strategy. What he's saying is, in general, there's a huge fixed cost to building any of these form factors. You need to amortize that cost over making a lot of these things. So rather than making a couple thousand of each of these specialty robots, you can make tens of millions of the same robot and just allow it to do these different tasks by reprogramming. That sort of scale is the same thing you see in like a cell phone or something, right? Instead of these kind of artisanal, like one-off cell phones that would be very expensive, Apple and Samsung and Google and others make millions of these things, and they're able to bring the cost down because they make so many of basically the same thing over and over again.
I would say the humanoid aspect is also very appealing because people can teleoperate it very easily. And so it's a data collection thing that is extremely helpful because people will be able to obviously very easily teleoperate it. I think that's usually overlooked. There's, of course, the aspect you mentioned, which is like the world designed for humans, etc. So I think that's also important. I mean, I think we'll have some variations on the humanoid platform, but I think there is a large fixed cost to any platform. And then I would say also one last dimension of it is you benefit a ton from like the transfer learning between the different tasks. And in AI, you really want a single neural net that is multitasking, doing lots of things. That's where you're getting all the intelligence and the capability from. And that's also why language models are so interesting, is because you have a single regime, like a text domain, multitasking all these different problems, and they're all sharing knowledge between each other, and it's all coupled in a single neural net. And I think you want that kind of a platform, and you want all the data you collect for leaf picking to benefit all the other tasks. If you're building a special purpose thing for any one thing, you're not going to benefit from a lot of the transferring between all the other tasks, if that makes sense.
So what Andrej is talking about here is not being lazy and basically saying like, oh, let's write the program once and have it be able to be, put out in a bunch of different ways. What he's saying is that large language models, and in particular large neural networks, like to have a diversity of data. In fact, he talks more about this later on, about mode collapse and stuff. But what you really want is you want a lot of different kinds of data, not a lot of the same kinds of data, but a lot of different kinds. If you use over and over again the same kind of data, just show it pictures of dogs and cats over and over again, it's never going to understand what a giraffe is. And actually, it will be worse at identifying dogs and cats than if you throw in zebras and horses and giraffes and stuff. The more data you can give it, in an analogous way to the way the human mind works, if you give us more diversity of data, we become smarter and are able to synthesize more knowledge. Same thing happens with a large language model. So what you want to have, what Andrej is saying, is that you want to have a single form factor with more or less the same neural network inside of it that's being trained on a whole diversity of tasks, and that diversity of tasks will allow the neural network to be smarter than it would have been if it had only been trained on a specialized task. Really interesting result, but it's been proven out over and over again in recent years. Next, Andrej gets into the psychology of the humanoid form factor and basically argues that rather than have weird looking creatures and stuff like that, that humans will interact with something that looks like a human in a better way than they will with things that don't look like humans. And I think he's onto something with this. I think the psychological aspect of humans relating to a humanoid form factor, or potentially a dog form factor or something like that, but that's very important to the ease of adoption of this new technology into our lives.
Understand that maybe you want to talk to it. And I feel like the psychological aspect also of it, I think, favors possibly the human platform, unless people are like scared of it and would actually prefer a platform that is more abstract of like some. But then I don't know if there's some kind of like an eight-wheel monster doing stuff, then I don't know if that's like more appealing or less appealing.
It's kind of like, it's interesting that I think that the other form factor for the Unitree is a dog, right? And it's almost a more friendly or familiar.
Yeah, but then people watch Black Mirror and suddenly the dog flips to like a scary thing.
Yeah.
So it's hard to think through. I just think psychologically it'll be easy for people to understand what's happening.
And then Andrej turns from embodied AI and Tesla full self-driving to why transformers are a beautiful technology, and also how we're going to overcome the data bottleneck that is slowing down the pace of AI development right now.
A lot of like the tools are available. And transformers are this beautiful like blob of tissue. You can just get just arbitrary tasks. And you just need the data, you need to put it in the right form, you need to train it, you need to experiment with it. You need to deploy it, iterate on it. That's just a lot of grunt work. I don't know that I have a single individual thing that is like holding us back technically.
Where are we in the state of large blob research?
Large blob research?
Yeah.
We're in a really good state. So I think, I'm not sure if it's fully appreciated, but like the transformer is like much more amazing. It's not just like, it's not just another neural net. It's like an amazing neural net, extremely general. So for example, when people talk about the scaling laws in neural networks, the scaling laws are actually to a large extent a property of the transformer. Before the transformer, people were playing with LSTMs and stacking them, etc. You don't actually get like clean scaling loss, and this thing doesn't actually train and doesn't actually work.
I think it's worth calling this out. LSTMs, RNNs, things like that, recurrent neural networks, etc., they had a problem with vanishing or exploding gradients. And basically the problem was that you looked at things over time, which is why it was called a recurrent neural network. But at each stage when you were doing gradient descent, you were having to do a multiplication step and multiplying, two small or big numbers like 0.1 times 0.1 gives you a lot smaller number, 0.01. So you're losing 10x of the value, and eventually those numbers can go to 0 or they can explode to infinity. And so transformers overcame that with the architecture, and that to this day is one of the major advantages of transformers, is that they don't have this vanishing/exploding gradient problem. They're able to train much longer, and that means that they're able to scale out their training and create these million token context windows and stuff that just simply wasn't possible with these other technologies.
It's the transformer that was the first thing that actually just kind of like scales. And you get scaling loss and everything makes sense. So it's this like general purpose training computer I think of it as kind of a computer, but it's like a differentiable computer. And you can just give it inputs and outputs and billions of it, and you can train with backpropagation. It actually kind of like arranges itself into a thing that does the task. And so I think it's actually kind of like a magical thing that we've stumbled on in the algorithm space. And I think there's a few individual innovations that went into it. So you have the residual connections, that was a piece that existed. You have the layer normalizations, that needs to slot in. You have the attention block. You have the lack of these like saturating nonlinearities like tanh and so on. Those are not present in the transformer because they kill gradient signals.
This may be a little bit geeky, but ReLUs, or rectified linear units, are actually critically important to modern neural networks because sigmoids and tanh and stuff saturate. In other words, they're kind of like an S-curve. You have to have a nonlinearity in a neural network in order for it to work. In other words, it can't just be a straight line. But the problem with something like an S-curve is that it works great in the middle. That's very, very sensitive. But when it gets out to the edges, it saturates. It gets closer and closer and closer to 1, and you're never going to reach 1, but you can have a lot of signal that's just in this very, very long saturated area. You want to get rid of that, and ReLU, or rectified linear units, in other words, something that's 0 if it's less than 1 and is the number if it's greater than 1, is much more effective. Also very, very much faster to calculate because it's like 0 if it's less than 1 and it's the number if it's greater than 1. You're not having to do any complicated math to do something like that. So the discovery that you could use something as simple as a rectified linear unit was actually huge in the advancement of these deep neural networks.
So there's 4 or 5 innovations that all existed and were put together into this transformer. And that's what Google did with their paper. And this thing actually trains. And suddenly you get scaling laws, and suddenly you have like this piece of tissue that just trains to a very large extent. And so it was a major unlock.
So that's Andrej's ode to the transformer architecture. I still personally think there's a need for another, some sort of fundamental, or again, some sort of synthetic breakthrough. In other words, having a bunch of different pieces that we have right now that are put together in a different way to create a new architecture. I wish I was smart enough to know what that is. But anyway, I feel like we need one more of those to really get to AGI. But speaking of synthetic, Andrej finishes off this section by talking about synthetic data and the challenges of data collection and the challenges of really understanding human thought in order to get to artificial general intelligence, or AGI.
And we're out of internet data. And so the questions are really around like synthetic data or more expensive data collection.
So I think that's a good point. So that's where a lot of the activity is now in LLMs. So the internet data is like not the data you want for your transformer. It's like a nearest neighbor that actually gets you really far, surprisingly. But the internet data is a bunch of internet web pages, right? It's just like what you want is the inner thought monologue of your brain.
Yep.
That's the ideal
The trajectories in your brain.
The trajectories in your brain as you're doing problem solving. If we had 1 billion of that, like AGI is here.
So what Andrej is talking about here is a local minimum. He says it's your nearest neighbor. In other words, this internet data, which is the output, the thought of humanity, it's not really the thought, it's the, finish of the thought. You think about writing a paper or writing a response, and then you write the response. What he's saying is we need to capture that actual thought process that's inside people's heads, and then we would get to AGI. That's a really, really interesting take. But the important part here is that he's saying that internet data is like a local minimum. So if you imagine you're trying to get to this point, the real minimum over here, and what we're stuck at is this other minimum, which is close to this minimum, but is substantially higher. In other words, the energy is much higher. We want to get over the hump and down to the real part of human thought, the real trace of human consciousness, and then we can get to AGI very, very quickly.
Speaking, to a very large extent. And we just don't have that. So where a lot of activity is now, I think, is we have the internet data that actually gets you like really close, because it just so happens that internet has enough of reasoning traces in it and a bunch of knowledge, and the transformer just makes it work okay. So I think a lot of activity now is around refactoring the data set into these inner monologue formats. And I think there's a ton of synthetic data generation that's helpful for that. So what's interesting about that also is like the extent to which the current models are helping us create the next generation of models. And so it's kind of like, the staircase of improvement.
How much do you think synthetic data is, or how far does that get us, right? Because to your point on each model helps you train the subsequent model better, or at least create tools for it, data labeling, whatever maybe. Part of it is synthetic data. How important do you think the synthetic data piece is? Because when I talk to people, they say, yeah.
I think it's the only way we can make progress is we have to make it work. I think with synthetic data, you just have to be careful because these models are silently collapsed is like one of the major issues.
So Andrej's going to talk more about this, what he calls silent collapse. I call it mode collapse. But basically he's saying what happens is as these large language models absorb data, what they tend to do is they tend to compress it, right? That's the whole point of what they're doing. They can't contain all of the knowledge of the world in an uncompressed format, just like a human brain can't do that. So it compresses it and compresses it. And the problem is when you then generate synthetic data, what you do is you're generating data based on this compression, and that data will also be less diverse than the original data. And then if you made like, imagine like another layer on top of that, at each level, you're collapsing the amount of diversity and the breadth of knowledge, and it's collapsing and collapsing and collapsing. I call it mode collapse. He calls it silent collapse because you can't really see it. He's saying if you do something individually, if you ask ChatGPT a single question, you don't notice it. But if you look at the statistics of the way that it answers in a very predictable manner, and that is a collapsed manner. And so you're losing a bunch of information that you want, and combating that to create synthetic data is the major challenge right now.
So if you go to ChatGPT and you ask it to give you a joke, you'll notice that it only knows like 3 jokes. That's like the only, it gives you like 1 joke, I think, most of the time, and sometimes it gives you like 3 jokes. And it's because the models are collapsed and it's silent. So when you're looking at any single individual output, you're just seeing a single example. But when you actually look at the distribution, you'll notice that it's not a very diverse distribution, it's silently collapsed. When you're doing synthetic data generation, this is a problem, because you actually really want that entropy. You want the diversity and the richness in your data set. Otherwise, you're getting collapsed data sets. And you can't see it when you look at any individual example, but the distribution has lost a ton of entropy and richness. And so it silently gets worse. And so that's why you have to be very careful, and you have to make sure that you maintain your entropy in your data set. And there's a ton of techniques for that. As an example, someone released this persona data set as an example. The persona data set is a data set of 1 billion personalities, like humans. Like backgrounds.
Yes, I saw this, yeah.
I'm a teacher, or I'm an artist, I live here, I do this, etc. And it's like little paragraphs of like fictitious human background. And what you do when you do synthetic data generation is not only like, oh, complete this task and do it in this way, but also imagine you're describing it to this person, and you put in this information, and now you're forcing it to explore more of the space, and you're getting some entropy. So I think you have to be just very careful to inject the entropy, maintain the distribution, and that's the hard part that I think maybe people aren't like sufficiently appreciating as much in general. So I think basically synthetic data, absolutely the future. We're not going to run out of data, is my impression. I just think you have to be careful.
So on that note, we'll wrap up this video. It's already plenty long. And like I said, Andrej goes on for another 22 or 23 minutes talking about other topics. We'll save that for another day. I hope you found this interesting. I find it absolutely fascinating to listen to somebody who's not only this brilliant, but has been doing this stuff, basically his entire professional career in a multitude of different ways. So he knows large language models. He knows the transformer architecture inside and out. He's used it not just for disembodied AI like large language models, but also for embodied AI, both in full self-driving and in the humanoid form factor. So he has a ton of insights into the way that AI is going, both embodied AI in the form of robots like cars and humanoid robots, and also in disembodied AI in the form of large language models. And his message, as you might hear, is generally optimistic, and that's carried over into the second half of the No Priors video. It is a wonderful video. Like I said, please do watch the whole thing, because I'm just pulling out pieces of it. It's very much worth the 45 minutes to watch it. All right, so that's what I've got. Let me know in the comments what you think about all of this. If you have any questions you'd like me to answer, I'd be happy to do that. And of course, Andrej, if you ever want to come on my channel, I would be honored. And finally, a big thanks once again to Geology for sponsoring today's video. Be sure to check out my link in the description to save 70% off your skincare trial set, and I'll see you in the next video. Bye-bye.